Okay, kids, we're getting into special segments, and we're going to do a lot of stuff with that. There's a lot of new terms and new theorems and properties you need to identify with each special segment. We're going to have to do the video lesson a little differently. I will be showing some or using some materials that you might not have, so I just need you to make sure your drawings are about accurate and you have the key information that I provide for you that I signify on the notes. So some of this is going to be reused. We're going to use prior knowledge to help you problem solve. Like perpendicular lines, we have already discussed. These are just basically lines intersecting, forming right angles. That's just my abbreviation. That okay. Bisects we've talked about too. Most of y'all think of it as cutting in half, but another way to think of it also is that it divides into two congruent halves. Now in class we are going to do a patty paper activity, and I will kind of show you that with some of the examples, but just make sure you get your drawings correct after I do the patty paper part. So before we do bisector, we talked about last 6 weeks. We looked at the equation for that. A perpendicular bisector is a line, segment, or array that passes through the midpoint, I'll abbreviate that, of a side of a triangle, and I would normally abbreviate that too, but I'll show you what I write. Usually I just use the delta symbol to show triangle, and it's perpendicular to that side. So for the patty paper purpose in class, I'm going to have y'all look at different types of triangles and construct different types of segments using just the patty paper, no other tool. And this is a little off, but basically, let's say if I trace this triangle and I have triangle BIG. If I want to find the midpoint, because we need the perpendicular bisector to go through the midpoint, I can fold the patty paper so point or the vertices G and B coincide. They're basically on top of each other. Alright, so to do that, I create a little crease, and I see this line segment here. I'm going to use my protractor just for a straight edge to trace that line. And show that it's a perpendicular bisector. I'm going to put the box, and I'm going to have to add the tick marks to prove that M is the midpoint. So basically here's that same triangle overlaying. I'm just going to fold it, see where that midpoint should have been, so that as if I was to trace the midpoint, and use my protractor. If you have a ruler or some type of straight edge, this would help. And we are constructing a perpendicular bisector. Now, by doing that, I'm showing that this segment here is a array here, and it's continued on. And I have the box to show it's perpendicular, and I have the tick marks to show that it's a perpendicular bisector. Well, with the perpendicular bisector, there's a theorem, there's a relationship that occurs, that happens whenever you have perpendicular bisector. And that is that any point on a perpendicular bisector of a segment is what we call equal distance from the endpoints of the segment. Now the converse of this is true as well, and I'll explain that in our little example. So let's say same thing. I'm going to trace the segment CD. And in doing so, we got that point, we got the C, we got the D. I'm going to fold the segment so the endpoints coincide, they're on top of each other, to create what would be the midpoint of that segment CD. So midpoint looks like it is, sorry about this, as such. And I'm going to put my tick mark to signify it's the midpoint. I'm going to move this M over a little bit because I know what I'm doing here. I'm going to end up drawing a line going through that midpoint, and I want it to still be perpendicular, so I want it to be at a 90-degree angle. And I'm doing this to show you the relationship. So the perpendicular bisector theorem states, the 5.1 theorem states that any point on the perpendicular bisector. So I'm going to put a point above the segment CB. It's on the perpendicular bisector. Forgot my box. I'm going to name that point A. any point on the perpendicular bisector is equal distance to the endpoints. Meaning, if I was to draw the segment from that point on the bisector to the endpoint C, and from that point to the endpoint D, these two would be equal distance, meaning they would be congruent. They have the same measurement. So I could have another point. Let's say I put a point below the segment CD. Label it B. The distance from B to the endpoint C is going to be the same distance from B to the endpoint D. Sorry about that. I knew that was going to happen. So they would be equal distance to the endpoints. Let's go off. I apologize. 3 tick marks. 3 tick marks. So basically, since I know that AB is perpendicular to CD and CM is congruent to MD, because we have a perpendicular bisector, then I know that any point on that perpendicular bisector is to be equal distance to the endpoint. The converse of this is true as well, meaning if I have a point that is equal distance from the segment, from the endpoints of the segment. So if I had, like, let's say I knew, without knowing this is a perpendicular, I knew that the distance between the endpoints to that point and that point were equal distance, then I would identify, or I could conclude that those points had to be on a perpendicular bisector, because that's the only time that that occurs. So an example that you would have, or the way you would be assessed on this, let's say, and I need to draw this, let's say you had a triangle, say we have triangle XYZ. Okay, so I'm just going to draw triangle XYZ. And here's my X, here's my Y, here's my Z. And I tell you that the distance from X to Y, okay, is congruent to Y to Z. Basically creating that sausage triangle. And if I create the segment going through Y to X to the side XZ, excuse me, then because I know these are equal distance, then I know that XY is congruent to YZ because they're equal distance. And I'm telling you that. Well, for example, let's say I have 2x plus, or 2x minus 5. And it's equal to 3x over here minus 11 for YZ. So then, because they're equal distance, I could set up the equation 2x minus 5 equals 3x minus 11. And then solve for x. Okay. Basically, you would end up 6 equals x. Okay. So as long as you know it's equal distance, then we know that this would have to be a perpendicular bisector. The segment, or the line, and I would need another point to name it. YM would have to be a perpendicular bisector for it to be equal distance to the endpoint. So this would also have to be a midpoint, M, to that side XC. Alright, so what's key that you have to know is definitely the definition to a perpendicular bisector. You need to know points on a perpendicular bisector, this theorem, and know that the converse of it will remain true as well. And then a new vocab will be concurrent lines. And I need to kind of show that to you. Concurrent lines. Basically, these are 3 or more lines that intersect at a common point. Alright, so basically, let's say I have a point. Got a line that goes through there. Another line through that point. And a third line. If I have 3 or more that intersect at the same point, at a common point, then we call those lines to be concurrent. So that's the new vocab that you need to know. And your point of concurrency is the point of intersection of the concurrent line. So basically, that little point that I drew on here would be your point of concurrency. Now, this is new, and you're gonna have to identify or relate circumcenter, the point of concurrency for the perpendicular bisectors. So, and I'm gonna show you an example of that here on the other side. Perpendicular bisectors of a triangle. So, circumcenter occurs only with perpendicular bisectors of a triangle. So on the other page, if you flip it over, I just want to look at this theorem real quick. Alright, so if I have a perpendicular bisector, meaning what I'm going to do is I'm going to create the perpendicular bisector of every side. And I'm going to use it with my patty paper. And I'll probably just show this with you with the patty paper, because I know I'm going to be pressed for time. Alright, so if I trace this triangle, we have B, we have A, and we have C. Alright, so I'm going to create the perpendicular bisector of every side. So first I'm going to do the side AC. So I want to make sure C and A coincide, create that perpendicular bisector. I'm hoping you see this is the midpoint. We see that segment right there. I'm just going to trace that perpendicular bisector right there. Alright, now I'm going to do the same thing for BC. Okay, so I'm just going to fold it again, but now I'm going to fold it so C is on the endpoint B, that they coincide. Make sure they line up, and then like that, make that one an X. There is a perpendicular line. I'm going through that crease, 2 tick marks. Alright, and I'm going to do the same thing for side AB. So there is that line. They coincide. Boom. Make that Z. This was M. Make this Z. 2, 3. 1, 2, 3. Perpendicular bisector. Alright, where the perpendicular bisectors intersect, okay, where we have a point of concurrency, we have 3 concurrent lines because they're going to intersect right there in that point. I already have a C. We're going to make that, let's see, Y. Okay, so that point where those 3 perpendicular bisectors intersect, that is called our circumcenter. Okay, the reason why it's called a circumcenter is because when you circumscribe a figure, basically, if I had a compass, I could do this. If I was to put this triangle inside a circle, and I don't know if I'm going to be able to draw this correctly, but because it's going to be off, basically like that. So if this triangle was circumscribed, then the center of our perpendicular bisectors, where the circumcenter right here, the center that we have here would be the center of the circle. And the circumcenter only exists when perpendicular bisectors intersect each other, and at that point of concurrency, you would have the circumcenter. And so we have a theorem. There's a relationship that occurs with this, and I'm gonna try to, let's do it on here. If I looked at the distance, okay, from the vertice to that circumcenter, so this is my Y is my circumcenter. So if I looked at my distance from Y to the corner, to the vertice X, A, excuse me, and then to the vertice C, oops, I was thinking about patty paper, and then to the vertice